So thank you for the introduction. Yeah, we got it. And thank you, Dr. Cho, for actually warming up the audience for me. I will have less time explaining the concept. So I will be talking about the smart textiles in general. And if you think about it, smart textiles are a very attractive platform for integration of various sensors. And nowadays we undergo the whole boom of the continuous health monitoring solutions such as smartwatches, various smartphones. And if you think that textiles surround us 24 hours, either as clothes that we wear or as like upholstery in our cars and our phones, so it's a very attractive idea to put some sensors inside. But at the same time, we don't really see them in our everyday lives, so the user acceptance is still very low. There are published papers, there are even some commercialized solutions. Like you can see here, the smart t-shirt, it's actually produced in Montreal, so I know them pretty well. But you can right away see the problem is that small box on the side of the smart shirt. So all the functionalities are actually introduced and the post-processing steps. The textiles are used just as a host to hold the electron. And the whole idea is to try to adopt already existing solutions for rigid electronics to some kind of flexible substrate. And then you need a protection against elements, which means encapsulation, which means in turn big bulky pouches that just not comfortable to wear. People don't want to wear this. And moreover, we need additional functionality. If we look at now what we have, everybody gives you ECG and activity levels from the accelerometer. Well, your phones and watches can already do that. We need new functionality. And that's why we were actually working for respiration monitoring. Since it's helpful not only for the athletes, but for the prevention of many chronic diseases such as asthma, pneumonia, sleep apnea, but most important that for the newborn infants, about 10% of them actually require constant monitoring during the first 24 hours. And how it is done now, it's basically the nurse observing them by the eye, constantly looking at them. And the respiration solutions that already exist now, they divide into two big groups. They either easy to use, such as like pulse oximetry or deducing from ECG data, or using some straps and piezoelectric belts. But that's all includes electrodes that somehow attach to your body. Sometimes it can be tolerable, but not for newborn infants, for example. Or on the other side, you have complex techniques that don't require contactless techniques, such as impulse radio radars, for example, or the methods based on fiber Bragg ratings. They work nice with a few drawbacks. Well, they need complex equipment to generate and analyze the signal. But what is more important, then confine the subject, the user, to a very limited zone. Either it's the focal point of the antennas, or it should be lying in a bed with a, once again, fiber around them. So our goal was to develop a mobile contactless solution for this application where the comfort is the topmost priority. And for that, we were even willing to sacrifice. So to do so, we had to reevaluate our approach to smart textiles. If we think about it, what is the unit building block of any textile? Well, it's a thread that composes the textile, and the thread of the fiber. And who has the expertise in fibers? Well, it's optical fiber manufacturing industry. We already know that for the telecom, we can combine various materials. We can take glasses, polymers, semiconductors, metals, combine them in a very well-defined and preserved structure and draw them kilometer lengths. That's what we do, right? So why not to use those to provide functionalities on the level of individual fiber to create true future smart textiles? And that's what we did. And when I say optical fiber, you instantly think, hey, there should be a laser somewhere. Well, not necessarily. For this sensor, we use the optical fiber to make a hybrid spiral antenna that you can see here integrated on the chest level, gives you some Iron Man look, if you wish. So the fiber itself is a silica glass capillary with an external coating of polymer, polyimide actually, that can provide you additional protection of the elements. You can make it super hydrophobic. On the inside, it's a liquid state deposited silver layer, 150 scale. So the resonance frequency was chosen 2.4 gig to be able to comply for the ISM band, Wi-Fi and Bluetooth. So what actually happens when you breathe? It's the shift of the resonance frequency. Actually, this is pretty much known to anyone working with implantable antennas. So you bring your antenna next to the body, it undergoes a frequency shift. In our case, it's induced by two factors. Well, there is a stretching of the t-shirt, but not the fibers. The silicon glass fibers, they don't stretch under normal conditions. But the arms of the spiral will change the geometry. They're going to part, and this will naturally change the resonance frequency. But what is more important, and actually more pronounced, that when you breathe in, you take in air, the dielectric constant of your lungs is going to change drastically from roughly 50 to 20, depending on inflated and the deflated lungs. And this gives rise to a big central frequency shift. So you can see here in various scenarios like sitting, standing, and lying scenarios, for deep and hollow breathing, this frequency shift could be as much as 200 megahertz. And even for shallow breathing, it's 10 megahertz, which is actually as wide as a channel of Wi-Fi or Bluetooth. And just from that, you can see, for example, on the latest picture, two different volunteers breathing differently. We can say that like one is taking more sharp breaths, another is breathing more slowly, more relaxed. And that's all good, but to measure the frequency shift by itself, you would need a spectrum analyzer, you would need a network analyzer. It doesn't really goes with the mobility criteria. So that's why we switched for the Bluetooth networks. Actually, we're using commercial Nordic semiconductor module due to this size. And what we are looking at is RSSI levels, basically the signal level to the device, in this case a tablet. Now, as soon as you induce a frequency shift when you breathe in air, you're going to lose some received signal. And that's exactly what happens. Now you can see in dotted gray lines is the raw data that we acquire. And this absolute level signal is not that relevant. In a way, it's going to be influenced by many ambient factors. But since you're looking for repetitive pattern, you're looking for the respiration rate, you can use various data treatment algorithms, such as peak detection algorithm, to detect when the inhalation and exhalation happen. Because you can see here what the typical signal looks like for the standing and sitting scenarios. It's also can be used for slow breaths, for slow breathing, fast breathing, and recently we've implemented a new peak detection algorithm that allows us to extend the reading range up to 3 meters away from the patient or the subject. And you can see here that yes, the absolute value of the signal is going to change, of course, but since you're looking to the peaks, you can still deduce the data. And we are less lucky than Dr. Cho. We didn't go under clinical trials. So when I say male volunteers, it's likely me or some of my students. But then again, it's completely uninvasive. So in fact, we don't require direct skin contact. So in our experiments, I'm wearing the t-shirt on top of another t-shirt. I don't really need skin contact. And you can see that for different test subjects, the signals are somewhat similar. Now, okay, we are from engineering school, so we have certain problems with the male volunteers. Yeah, and the signal readout is not that good. Well, the solution is that we had to still study the position of the sensor. Of the sensor since, well, for now it was positioned pretty arbitrary. And moreover, different people tend to breathe a bit differently from the biomedics point of view. Some tend to contract more the diaphragm using the belly, the others breathing more with the chest. So all this has to be addressed. But in general, we can say that, yeah, the respiration pattern can be actually acquired using this very simple method over the standard Bluetooth network over like 3 meter distance. It's applicable for fast and slow breathing. We don't require direct skin contact. And what is more important, the overall the fabrics are undistinguishable with integrated fibers from typical other fabrics. If we're speaking about perspective, well, we can try to go from glass fibers to polymer fibers. It's a natural solution, but then the chemistry becomes a bit more difficult since you have to activate the surfaces to be able to actually attach your silver electrodes to the polymers. It's more tricky. As you saw, we need to optimize the position of the sensor. Maybe couldn't the bigger number of the sensor, nothing stops you have an array of antennas and actually measuring the signal between them. Clinical trials, well, the holy grail of biomed. Well, we are going that with the hospital now, but it's taken very long. It's been almost a year by now, and this goes through the ethics committee. test subjects, and I think everyone knows how it goes. So we're not there yet, but we definitely need to compare to the gold standards. But at the same time, we already know that we're not going to be as precise as methods that involve like direct measuring airflow, because what we are measuring is a chest movement. So in fact, if there is no air in here, we won't be able to tell if it's just the chest that expands. So there is these drawbacks. And well, finally, as you can understand, this is quite a multidisciplinary project that involves experts in many fields: chemistry, material science, wireless communication. And it was supported by the grants of Government of Canada, and it's a joint effort of two groups: the group of Professor Younès, group of Professor Amine,